This is part 2 of hypothesis testing for multiple sample studies. It is in Module 2, Comparing Groups. An ANOVA is an overall test, so it only tells you if some of the groups are different from each other. In order to determine which groups are different from each other, you must do multiple t-tests. Some of you may wonder, what if we did 3 t-tests instead of an ANOVA? We could set our significance level at 0.05 for each of the 3 tests and compare each possible pair of groups. However, if each null hypothesis were true and we tested each of the 3 hypotheses, the probability of rejecting at least one true null hypothesis is now 0.143 instead of 0.05, meaning our probability of committing a type 1 error is now 14.3% instead of 5%. This is because each test is independent, and so the probability of committing a type 1 error is 0.05 for each test. The more tests that we do, the more likely it is to commit an error. This comic demonstrates the problem of doing a bunch of t-tests when you shouldn't. You can peruse it at your leisure. The basic idea is that our significance level, the probability of type 1 error, should be for all planned comparisons, not for each planned comparison. As you can see, as the number of groups increases, the probability of type 1 error increases exponentially. Therefore, if our family-wise error rate is 0.05, the significance level for the overall test, or ANOVA, we need to do something before we can do multiple t-tests. Therefore, for multiple sample studies, hypothesis testing is a 2-step process. 1. Perform the overall test of significance, and 2. Do pairwise comparisons if the overall test was significant. In order to keep the family-wise error rate at 0.05, we must adjust the significance level for our pairwise comparisons. That is, our 2-sample t-tests using MSE as a common variance. One such method is called the Bonferroni adjustment. In this adjustment, we divide alpha, the overall significance level, by the number of planned comparisons. For example, if our overall significance level is 0.05 and we have 3 groups and thus 3 comparisons, the adjusted significance level for the t-tests, the pairwise comparisons, would be 0.0167. Therefore, we would compare the p-values from the pairwise comparisons to 0.0167 instead of to 0.05. Let's look at this in the context of the first study example. In this example, we have 3 groups to compare and thus 3 pairwise comparisons. Remember that our overall hypotheses assume that all of the groups have the same mean, while the research hypothesis states that some pair of groups does not have the same mean. From the first hypothesis testing lecture, we found our p-value to be 0.005778, which is less than the significance level of 0.05. Therefore, we rejected the null hypothesis and concluded that there is enough evidence that the true mean sleep hours are different for at least 2 of the groups. However, this does not tell us which groups are different from each other. In this example, we have 3 t-tests, assuming MSE is common variance, to perform. We compare the p-values from each test to the Bonferroni adjusted significance level of 0.05 divided by 3, which is 0.0167. Now, don't get scared by all these numbers. In Concept Practice 8, I've calculated these for you. However, I wanted to show you where the numbers come from. Let's look at the first formula. Remember that our standard error for unequal variance was the variance of the first group divided by its sample size, plus the variance of the second group divided by its sample size, all under the square root. If the variances of the 2 groups are the same, we can take off those subscripts. Using algebra, we can pull out the common variance, leaving us with the variance multiplied by 1 over group 1 sample size plus 1 over group 2 sample size, all under the square root. That's exactly what we have here, except now we're using the MSE from ANOVA as the common variance. You can see that it's the same in every t-test. To find the p-values, we use t.dist.2t, since the hypotheses are two-sided or not equal to. Remember that the degrees of freedom from the last slide for the MSE are 2044. In the first example, we type the function, then put in the test statistic, a comma, and the degrees of freedom, and then finish the function and hit enter. The same is true to calculate all the p-values. As a note, t.dist.2t only takes positive test statistics. So if your test statistic is negative, you can simply type in the positive value, or you can use the absolute value function, ABS, around the test statistic. We compare each p-value to 0.0167. Take a few minutes and determine whether each p-value is greater than or less than 0.0167. Please pause this video while you make this determination. For the first and third tests, the p-value is greater than 0.0167, so the null hypothesis is not rejected. For the second test, which is comparing 0 AP or college courses to 2 or more AP or college courses, the p-value is less than 0.0167. Therefore, the null hypothesis is rejected, and there is enough evidence to conclude that there is a difference in true mean sleep hours between high school students who did not take AP or college courses and those who took 2 or more AP or college courses. From the last lecture, the Kruskal-Wallis test is the nonparametric version of ANOVA. If that overall test is statistically significant, you should do pairwise comparisons using Dunn's test. However, instead of doing this on your own, I strongly encourage you to seek a statistician's help to perform these tests. Now let's look at study example 2. In this example, we have 3 groups: those who took the test with a pet present, those who took the test with a human friend present, and those who took the test with no one present. The overall hypotheses are shown on the slide. Remember that we assume that there is no difference in the true mean heart rate for adults doing a mental task with a pet present, a friend present, or neither present. We can also write this as the means for each of the groups are equal. Our research hypothesis is that the true mean heart rate is different for at least 2 of the groups. Remember, we can't specify which groups are different, so the research hypothesis includes all possible pairings of groups, whether that's listed out in long form, the first bullet point, or in shorthand, the second bullet point. Though you haven't yet completed concept practice 8, you will compare the p-value from the ANOVA you performed that concept practice to 0.05. If the p-value is less than 0.05, hint, it will be, you will reject the overall hypothesis and do pairwise comparisons. Remember that for pairwise comparisons, you are comparing the p-values to a Bonferroni adjusted significance level. As an aside, the reason you do not do step 2 if you fail to reject the null hypothesis for ANOVA is because by failing to reject the null, you're saying there's not enough evidence to say that any of the groups are different. Therefore, there's no reason to go on and test which groups are different. Remember the green jelly bean example? These 3 slides contain the hypotheses for the pairwise comparisons. Note that all of the tests are two-sided, so you will use t.dis.2t. I've calculated the test statistics for you, so you only need to use those and the degrees of freedom for the MSE to calculate each p-value. In concept practice 8, you will do an ANOVA for the heart rates from the study example. Remember that if the overall test is significant, you will need to do pairwise comparisons to determine which groups are different, remembering that a Bonferroni adjustment is needed for the comparison conclusions.